Everybody, this is Dr. Niger with a Physics Fundamentals screencast. This will be the first in a series that deal with electricity, Ohm's law, and circuits. This is going to be one of the intro screencasts. It's going to look at charge, potential difference, and current, including the variable symbols, formulas, and units for those different variables. All right, so let's start with charge. All right, so charge is calculated by using the formula Q equals N times E. All right, now charge, in chemistry, we would say that an ion has a +1, a +2, -1, -2 charge, which would indicate that there's an imbalance between the protons and the electrons. If there were more protons in the ion than electrons, we would say it's positively charged. If there are more electrons than protons, we would say it was negatively charged. And we generally went with those whole number conventions. But the reality is that a single electron does not have a charge of -1, right? Instead, it has a charge that is much smaller than that. So when we start talking about the flow of electrons, we need to be more specific about what that charge actually is. And that's where this formula for Q comes in. All right, so our unit here is going to be a new one for us. It's called the Coulomb, and it's represented with a large capital C. All right, that formula includes charge, which is Q. So Q is charge. It includes N, which is the number of, I'm going to call them unbalanced. Whoops, I left out my N. Unbalanced charged particles. All right, and then we end with E. Now, E does not stand for electron. E is a constant. It is the charge on a single charged particle. All right, so it can be positive if we're talking about an excess of protons, or negative if we're talking about an excess of electrons. 1.6 times 10 to the negative 19th coulombs. All right, so you can see that we have a very small value associated with a single subatomic particle. So instead of saying, for example, a fluorine ion is -1, all right, we should say a single ion has a charge of negative 1.6 times 10 to the negative 19th coulombs. All right, now we know that based on the structure of the atom that the electrons are free to move because they are on the outer shell of our atom, whereas the protons are not. So if we have an entity that's positively charged, it's because the electrons have left. We've lost some electrons, not because we've gained protons. So just remember that. All right. And then for our purposes, when we deal with electricity, all right, usually we're going to have excess electrons. So Q most often is going to be negative. Not always. You should read the problem. But for the most part, we're going to be dealing with charges that are negative. All right, so now let's move on to potential difference. All right, so potential difference, this is also known as voltage. All right, it's the pressure that pushes the electrons around our circuit. So it's the pressure that pushes the electrons in a specific direction. All right, and it's due to attraction or repulsion in our circuit. All right, so what does that really mean? Well, when we have a voltage source, a battery is a great example. All right, there's a positive terminal and a negative terminal. And when we hook that battery into our circuit, the electrons in our conductor wire are going to want to move from the negative terminal of the battery where there's repulsion around that circuit to the positive end of the battery because they are attracted. Now, the greater the difference between the positive end and the negative end of the battery, the higher the voltage.
All students should be in the front lobby. Bus 39. Students who take bus 39 will take bus 5 at 1:30 or 1:40. Again, all students should be in the lobby.
Sorry about that. I don't want to start over, so we're just going to go with it. We had a half snow day here today, and that's what's going on with our buses. All right, so back to our battery. If we have a big difference between the positive and negative ends, we say that we have a higher voltage. That means there's more pressure, so it's going to push more current around that circuit. All right. Now, when we measure or calculate the voltage, all right, we need to know two things. We need to know the potential energy that is available per amount of charge. All right, so this is our potential. Oh, whoops, let me fix that. Sorry. Electric potential energy, and we need to divide that by the amount of charge. All right, that electric potential energy is similar in concept to gravitational potential energy. When we want to move a charge against the gradient. So in other words, if I want to move a negatively charged particle towards the negative end of a charged gradient, it's going to require force because the negative particle doesn't want to go there. All right, so I'm going to have to apply a force, and if I move it over a distance, that means I've done work. And I know from our earlier investigations that work can be converted into either potential or kinetic energy. Right? If we're lifting something to a height, that work is converted into gravitational potential energy. If we elongate a spring, that work is converted into spring potential energy. If we move a negatively charged particle towards a negative charged area, then we are doing a work, and that turns into electric potential energy. All right, so to calculate the voltage, I need to know what that potential energy is and the amount of charge I'm trying to move. All right, so our unit here is a compound unit called joules per coulomb, which is what our potential energy divided by charge would give us, but we tend to most often use volts, which is a capital V. All right, so once we have charge and we have a push, all right, then we get our last piece, which is called the current. All right, the current is the flow of our electrons around the circuit. All right, it's a measure of the rate of flow, more specifically. All right, so we use the variable symbol I to represent current, all right, and it's going to be equal to the amount of charge that's moving. That's a terrible cue. Let me try that again. Divided by the time. All right, so charge divided by time. All right, now our unit here is a new one for us again. It's called an ampere, which is represented with a capital A. All right, and that ampere also can be listed as a compound unit of coulombs per second. All right, so again, that coulomb per second idea tells us that this is a rate calculation. Okay, so we should be able to figure out the charge if we know the number of particles and whether they're positive or negative. We should be able to figure out the voltage if we know the potential energy that's available and the amount of charge that we're trying to move. And we should be able to calculate the current based on the amount of charge that's flowing divided by the time over which we are measuring. All right, so we've got three formulas. I'm going to highlight these just so they stand out a little bit. All right, we've got this one, Q equals N times E. We've got voltage equals the potential energy divided by charge, and we've got current equals the charge divided by time. Okay? All right, so we're going to try a couple problems. These are pretty straightforward. Really helps to have a variable list because then you can immediately pull which formula you need. But because these formulas are new for us, you need to make sure you are paying attention to what is being given and using those units to identify variables. All right, so there is a current of 0.3 amps in a resistor. How much charge will pass through in 5 minutes? All right, so the 0.3 amps tells me it's current. Of course, the word current appears right before it too, which helps. All right, we have a time value of 5 minutes. All right, and we never keep it in minutes. We always convert it into seconds. So 5 minutes times 60 seconds per minute equals 300 seconds. All right, and then we're asked to find charge. All right, and charge is represented by the variable symbol Q. So this is what we're looking for. All right, so if I look, I do have a formula that has these three variables in it. Current is equal to charge divided by time. All right, so I'm going to plug in what I know. 0.3 amps is equal to the charge divided by 300 seconds. Multiply both sides by 300, and I find that my charge is equal to 90 coulombs. All right, so that's the charge. All right, the next question wants to know, well, then how many electrons is that? All right, so if we're looking for a number of particles, that's n. All right, so we now have Q, we have I, and we have T. And if I look, I have a formula that includes charge, the amount, and the charge per particle. So Q equals N times E. All right, so my 90 coulombs is going to be equal to N times that constant, 1.6 times 10 to the negative 19th coulombs. All right, we're going to divide both sides by E, and we're going to get a total amount of particles of 5.63 times 10 to the 20th. All right, it says electrons, so I'm just going to use that as my unit. All right, now that's a lot of electrons, but that's reasonable because each one has a tiny amount of charge. And if I have 90 coulombs of charge, then it's reasonable that I must have a lot of electrons. All right, let's try the next one. A power supply is set to 2 volts and is connected to a light bulb. How much energy would 3 coulombs of charge get to go through the light bulb? All right. So again, I'm going to do a variable list. This time I have a voltage value or potential difference, 2.5 volts. I've been given something that says 3C of charge, so that's Q, 3 coulombs. And I'm asked for energy. All right. So whenever you're asked to find energy, so the potential energy is what we're going to solve for. But if the electrons are moving, then that potential energy has been converted into kinetic. But the value is the same because of conservation of energy. So I'm going to be looking for U sub E in this problem. All right. So I have a formula that includes those. The voltage is equal to U sub E divided by Q. All right. So I plug in 2.5 volts. My unknown is that potential energy, and I have 3 coulombs of charge. So I multiply both sides by 3, and I end up with a potential energy of 7.5, and that's going to be joules. All right, remember the unit for energy is joules. All right, we move down to the second part, and it says, well, how much energy if we have 15 coulombs of charge? So we're going to do the same calculation, solving for that potential energy, starting with the same voltage amount, but this time instead of 3 coulombs of charge, all right, we've got 15 coulombs worth of charge that are moving. All right, so the energy needed to move that much charge is going to be equal to 15 times 2.5 or 37.5 joules. All right, so that's the energy that we would need to be able to move that much charge against a gradient of 2.5 volts. All right, one more problem. In 2 hours, 4,320 coulombs worth of electrons move through a light bulb that is plugged into a 120 volt outlet. All right. So what do we have? We have time. We have 2 hours. All right. Now, again, we never keep it in hours. So I'm going to go ahead and convert that into seconds. All right. And 1 hour is 3,600 seconds. So 2 hours is 7,200 seconds. All right. We also have 4320C. All right. That C, that unit tells me that that is charge. It's coulombs. So 4,320 coulombs of charge. All right. And we have a voltage of 120 volts. That's the potential difference that's coming from your plug. Okay. The first question wants us to find the current. All right. So we're looking for I for part A. All right, so if I look up my formula for I know that that flow is equal to the number of particles, or sorry, not the number of particles, the charge that's moving divided by time. All right, so in this case, I've got 4,320 coulombs worth of charge moving over 7,200 seconds. So that means that my current must be 0.6 amps. All right, so that's our first one. The next one now, how many electrons? All right, so now I want to find N. How many electrons are moving in that charge? And I know that the charge is equal to the number of particles times the charge per particle. All right, so 4,320 coulombs is going to be equal to my unknown times 1.6 times 10 to the negative 19th coulombs. All right, now, if you want to get specific, I could put a negative sign out front, all right, for my charge, because it is electrons. But if I do that, I need to put a negative sign in front of E. All right, so the negative sign is going to cancel, and I'm still going to get particles. Now, N should always be sign-free. All right, it's not positive or negative. It's just a number of things. All right, so I divide 4,320 by the value for E, and I find that I must have 2.7 times 10 to the 22nd electrons that are moving in this circuit. All right, and then finally, how much total energy was used by the light bulb. All right, so if I know the voltage and I know the charge that's moving, I can figure out what the energy requirement is. All right, so I'm going to be looking for U sub E for this last part. And I know that the voltage is equal to that potential energy divided by that charge. All right, so I have a 120 volt outlet. All right, some energy is then required to move 4,320 coulombs worth of charge. All right, so the amount of energy that I need is 518,400 joules. That's a lot of energy. So I'm going to need that much energy to move that amount of charge at the rate of 0.6 amps. Okay? All right, so these are, as you can see, pretty simple calculations. But because the terminology is new for us, the units are new, right? Don't sleep on these problems. Don't assume that they are going to be super easy. Just make sure you practice and you should be all set.